I'm going to be having a quick look and giving you a brief teaching session on acceleration. And of course, this is another practical application of calculus and the derivative. In our past teaching sessions, what we would have introduced you to is if we had a function s of t, that was actually almost modeling a real-life situation where we were modeling something called displacement, distance, or height. Yesterday, Liesel took you through how if we actually take the derivative of displacement as a rate of change, that would be regarded as how our distance is changing with respect to time. Now, if we think about that, changing our distance with respect to time, that gives us the velocity of a particle. So yesterday, that is what Liesel would have taken you through, is how the first derivative of one of these functions actually gives you the velocity of a particle. Now, what I'm going to be talking about this evening is what is to happen if we were to take the rate of change of velocity with respect to time. And I'm hoping that in class situations you have been actually introduced to this as the notion of acceleration. Now, the best way, guys, that I can actually get you to understand this is to have a look at three different situations. What I've done very quickly is I've put up a function in t. So s of t is 5t plus 10. So let's just say this is modeling the height of a particular particle after a certain amount of time. Now notice, if I work out the s of 1, that would be the distance or displacement after 1 second. That would be in meters, 15 meters. The s of 2, putting 2 into there, would be 20 meters. The s of 3 would be 25 meters. Now remember, just that straight thing is either giving me my distance, my displacement, my height of the particle. All right? So please notice that my answer is in meters, and that's important. We need to give the unit of measurement. However, if I take the derivative of this particular function, can you see that the derivative with respect to t would just be 5? And 5 is a constant. So that means that my velocity, initial velocity, is 5. My velocity at 1 is 5. My velocity at 2 is 5. Now notice that velocity is a rate of change of distance with respect to time. And that is why my answer is in meters per second. Can you see that here your distance was 15, it increased to 20, it increased to 25. So your velocity, okay, is constant at 5. Your rate of change is that it's changing 5 meters every second. Now see that because it's changing 5 meters every second, that's constant, so it's not accelerating. It's not getting faster or getting slower. However, let's have a look at a second situation. If I have a look at my displacement formula as being a quadratic, and I've chosen minus 2t squared plus 4t. Then on substituting 1, 2, and 3 in, this is telling me how many meters it's gone after 1, 2, and 3 seconds respectively. Okay? The particle has gone 3 meters, 4 meters, 3 meters. If I take the derivative, which is the rate of change of distance with respect to time, my derivative is minus 2t plus 4. Can you see that by substituting in a 0, my initial velocity is 4. At 1 second, it's 2. At 2 seconds, my velocity is 0. At 3 seconds, my velocity is minus 2. Can you see that my velocity is not constant? Okay, it's not constant. And in fact, can you see what's happening? It's going 4, 2, 0, minus 2. Okay, definitely not constant. But if I were to take my second derivative, which remember is going to be the rate of change of velocity with respect to time, can you see that the derivative of this expression is now minus 2? So my acceleration is now constant, and it's -2 meters per second, and because it's the second derivative, we write it with a little 2. Can you see that your velocity was 4, then 2, it's gone down 2. Then 2 to 0, it's gone down 2. 0 to -2, it's gone down 2. Your acceleration, okay, is -2, all right, meters per second. Notice, please, that your distance is in meters. Your velocity, or your first derivative, is always in meters per second, but your acceleration is in meters per second squared. Because it is the rate of change of velocity, with respect to time. Okay, with respect to time. And the last thing I want to point out is if I were to have a cubic, can you see that my first derivative, which is velocity, is going to be power 2. My second derivative, which is acceleration, is power 1. So can you see that the acceleration is not constant, but here we're getting acceleration, initial acceleration is 4 meters per second. Then at 1 second, it would be 10 meters per second squared, and 34 meters per second squared. So please notice that if you have a function which is of order 3 or higher, your acceleration will not be constant, it will also still be variable. So hopefully that's kind of put some clarity on what acceleration is. Remember, a function s of t is displacement, distance, or height. If we take our first derivative, that's a rate of change of distance with respect to time. That gives us our velocity, and of course velocity is just another word that we use for speed. And our second derivative is the rate of change of velocity with respect to time, and of course that's in acceleration, and our unit is in meters per second squared.